Hi everyone. It's been a very fun and useful program for both of us and for everyone in this room, I think. And Emirhan was very hardworking and was very passionate for his subject, and he did a great job. Now he will be presenting, after a crash course on category theory, equivalence of categories, abelian categories, and finally Mitchell's embedding theorem.
Hello everyone. Today I'm going to talk about category theory and Mitchell's embedding theorem. First, I'm going to make a basic introduction to category theory. Then I'm going to define the sameness concept of category theory, which are equivalences. But I'm going to explain why they're important in the presentation. Then I'm going to give an example of equivalences, Mitchell's embedding, and make a sketch of the proof. So, categories are generalizations of mathematical structures. Before giving the formal definition, to give you a concrete idea, I'm going to give you the examples. So, in a category, we have objects and morphisms between objects. And for example, the category of sets, we have as object sets and morphisms functions. And for example, groups, we have category objects groups and group homomorphisms. So in a category, every morphism has a domain and codomain. And each object has an identity morphism. And we have a composition of morphisms, which has left and right units, and it's also associated. So we have a definition of isomorphism. So we call a morphism an isomorphism. It has right and left inverses, and in this case we say they are isomorphic. And we denote the collection of objects, collection of morphisms between any object, like this. And we call it offset. But there is an important concept here, subcategory. We call S a subcategory of the category C when each object of S is also contained in the category C. And we call full subcategory if between any object of S and any morphism between these objects in C is also contained in S. What we mean by this is S does not have any missing morphism. And there's a basic example of a full subcategory, a category of abelian groups, which is a full subcategory of groups. So when we want to create relations between categories, we need functors. So a functor basically consists of an object Fa in D for each object A in C, and a morphism Fg in category D for each morphism G in category C. And functors have to preserve identity morphisms and compositions of morphisms. So when we want to create relations between functors, we need natural transformations. So a natural transformation consists of mappings. We show them object-wise. For each object of C, we have natural transformation. So components of natural transformations. So you can think of natural transformation like this. So it takes FC and gives you the GC. And when we consider a morphism in category C, this diagram needs to be commutative. What we mean by commutative is, so this composite and this composite must be equal. So this is the formal definition. We are not going to use this part, but yes. And we call it a natural isomorphism if all components are isomorphisms in category D. And there is a functor category from C to D, which has functors as its objects and as its morphisms, natural transformations. And there is a composite natural transformation, which we can define by component-wise composing them. So now we came up the point where we want to define the sameness of categories. So if we think, if we try to construct an isomorphism, we will have something like this. So this composite need to be equal to identity. So when we take an object and we came back to the R category, it must be equal to the same object in isomorphism. But this is a very strict definition for us. It's not useful. In this case, the category of finite dimensional vector spaces over R is not same as the category of Euclidean spaces R to that. And we don't want something like this. So we define equivalence. So we want the compositions to be naturally isomorphic to the identity factors. What we mean by this is when we start with an object A, and then when we came back to our category, we want it to be isomorphic to the starting object. So in this case, we also call F is an equivalence. So what is the important part of being an equivalence? So if we can show that two category is equivalent, then when we prove something in one of the categories, then we simultaneously prove for the other one, for the modified version, the transformed version of the proposition. We can prove it by no effort. And fortunately, there is a practical way to show that a functor is an equivalence. So we call a functor full if this morphism is a surjection, and faithful if it's an injection. So what we mean by this? So for any G between Fc and Fc prime, if there is an hash, it satisfies f hash equals G. It says a surjection, and if this hash is unique, we say it's faithful. So you can think like a bijection of homesets. And our proposition says that if we have a fully faithful functor, then C is equivalent to the full subcategory of D, which consists of objects of the form Fc. And there's a natural example and very important example of this equivalence concept, which is called unit embedding. Before introducing unit embedding, I need to give some definitions. So the covariant representable functor, which we show like this, it sends each object A to the collection of morphisms from C to A. So it represents C by giving us all morphisms which has domain C. And on the other hand, the contravariant representable functor is, so contra means we are reversing errors. It sends each object A to the collection of morphisms from A to C. Then the unit embedding is, so, and this is very general. You can see this. We didn't choose some specific category. We only choose any category. So the unit embedding takes an object, sends it to the covariant representable functor, and the proposition states that the unit embedding is fully faithful. So there is an equivalence between any category and the functor category from C to Z, the subcategory. Now, in our case, we want to construct an equivalence between abelian categories and left-arm modules, but due to the lack of time, I'm not going to delve into details about abelian categories, but I'm going to try to give you some intuition about abelian categories. So they are generalizations of category of abelian groups. For example, the first condition, it says each home set are abelian groups. This means that you can sum morphisms somewhere. And the second one says that category has a zero object and byproducts. So zero objects corresponds to the trivial groups in abelian groups, and byproducts corresponds to direct sums of groups. And third and fourth one says that it's a generalization of the isomorphism theorem in category theory, in group theory, isomorphism theorem. And finally, our term, we can state it. So it says, let's see, be an abelian category. So abelian, small abelian category. Small means you have your object, collection of objects and morphisms are sets. And we have a small abelian category. Then it says there exists a ring and fully faithful and exact functor C to R modulus. So exactness is also about abelian categories, but or algebra. But we are passing it. So you don't need to know exactness to understand my proof sketch. So, I know that most of you know R modulus, but I'm gonna give the basic definition of it. Okay? We say M is an R module if it's an abelian group and it has a scalar multiplication by left, and it has some also properties. So I want to try to give you an intuition of proof. So we take a functor category from C to D. Then we want it to have home sets abelian groups. So we mean this. We want to sum the natural transformations. And we suppose that there is an object which is a functor from C to D, so that the natural transformations from from I to I are constructs a ring. And then we have that for any home set, so for any functor, this home set is a module. So we can observe this by taking an element alpha and a ring element and composing them. We still being in the M. So this composition of natural transformations corresponds to the scalar multiplication by left in R modulus, basically. Now we can start our proof. So we take C as an abelian category. Then since C is abelian, the home sets are also abelian groups. So if you remember, this covariant functor was from C to set, but since these are abelian groups, it became from C to abelian groups, category of abelian groups. So we modify our unit embedding. Then we take a subcategory of the left exact functors L from the functor category C to AB, and we need to show that it's an abelian category, and the image of unit embedding is contained in L. Then we construct a contravariant functor H, which do the same thing with Yoneda. It takes and we need to show it's exact. So we know that a unit embedding is fully faithful, and we have shown it's exact. So we did the half part of the proof. So and in the second part, we want to find a functor from L to R modulus. So since we have proved L is an abelian category, its home sets are also abelian groups. And there is a L. We have to also prove that L has an object which is called injective cogenerator, and it's not trivial to prove it. So which basically does make this functor faithful and exact. So as you remember in the intuition part, these were modules, but we need to choose our as the endomorphism ring, as we did in the introduction part. Then this become modules, and we get our functor from L to R modules. So as we get the desired fully faithful and exact functor from C to R modules, so we have proved our theorem. And lastly, we can prove this lemmas for abelian categories, short five lemma, the five lemma, and the snake lemma, and more of them, by just only proving them in the category of R modules, because we have shown them they are equivalent, and it's easy to prove in R modules. And that was all. Thank you for listening. These are my references.